Okay, last class we left off we talked about physical properties, chemical properties, physical changes, chemical changes. In a physical change, the chemical does not change. It's the same chemical before and after. So things like phase changes, things like cutting something, breaking it into smaller pieces, those are examples of physical changes. Chemical changes, blowing stuff up, lighting things on fire. If we see a color change, that might be a sign of a chemical change. Other fun stuff like that. It's on these last couple of slides, and we went through a couple of examples. This is all very relevant for today's lab. One of the ways we can separate mixtures with physical changes is by distillation. I talked about this a little bit. I specifically said desalinization or something similar to that. So this is an example of how you might separate things out. We're not going to be doing this in this lab, but if you go on and take more labs, you'll probably do this at some point. So we've got a round bottom flask. It's called a round bottom flask because it's got a round bottom instead of a flat bottom. It's hooked up to this little manifold that holds it up and also helps direct the Bunsen burner flame so that it's not just scorching the bottom of the flask. We're heating up a salt water mixture in our distilling flask here. We've got a thermometer up here in the top just to check what our temperature is. If you get the temperature too high with some mixtures, then you'll end up transferring over more things than you want to. And then we've got a condenser here. The condenser has a hollow tube on the inside and then a water bracket on the outside. So water can go through the outside part so we can run cold water through. That cold water, as soon as this hot vapor hits this cold water part, it condenses, just like water on the outside of your big cup of ice water during the summer. And then everything that condenses gets collected into this receiving flask. In the case of this saltwater mixture, that would just be the water going over. Also with a saltwater mixture, you're not going to ever send the salt over, so it's not that big of a deal to have the thermometer. Another thing that you could do with a setup like this is you could, this is one that I did in undergrad. We took orange peels, tore it up into little pieces and put it into this distilling flask with some water, heated it up, and there's essential oils that are in orange peel, and those essential oils evaporate at a lower temperature than the water, and so we were able to collect orange essential oil over here instead of pure water. And then we had a little vial of orange essential oil. It smells pretty good. It's relatively safe, so a lot of essential oil distillations would be done this way. You can also do it with things like catnip, so you can make concentrated essence of catnip. There's not very much of that catnip essential oil in catnip, though, so it takes a lot. I've heard of somebody doing this. They had just like a little tiny vial of basically cocaine for cats. So like you put a drop out and cats from all over the neighborhood come running. So if you knew somebody that didn't like cats, put a drop on them, they would have a really bad time, I imagine. So that's one way that we could separate mixtures. We're not going to do that. Another way that you can separate mixtures is with filtration. So filtration, we've got filter paper here that's crammed into this funnel. There's fancier ways of doing this. If you remember our lab yesterday, we had the glass beads and the nickel beads. They were in those little funnels. There's also flat pieces of filter paper you can put into those funnels. So those would catch solids, but allow the water to go through. So if you wanted to separate sand out of a water mixture or just small particles, that's how you do it. This is an easier way to do it with this funnel. You don't have to have the more expensive Buchner funnels that we were using yesterday. And then you can pour a slurry or a mixture of things. You can see that there's a little bit of color to this. It's kind of grainy. There's probably activated carbon or something, or some chemical that's in there. And that'll be out on this filter paper, but the water or the liquid will go through. So that's another way that you can separate things physically. Okay, going back to something that we heard about on our first day, the law of conservation of matter. Matter, as you may recall, has mass and takes up space. So a lot of things are matter. The vacuum of space, matter. Light, not matter. People, chairs, smells, actually, matter. Okay, so things like that matter is not created, nor is it destroyed. There's no new matter that's produced from a chemical reaction. There's no matter that's destroyed in a chemical reaction, with one exception being nuclear reactions. In nuclear reactions, we do have significant changes in mass. We won't deal with nuclear reactions or nuclear stuff until the end of the class. So generally, we can assume when we're doing a chemical reaction, the amount of mass that we started with should be the same amount of mass that we ended with, but we might rearrange the atoms, the molecules. So mass before a reaction equals mass after a reaction. This assumes that we have still captured all of the mass. So like when you burn wood in your fireplace or having a barbecue out at night, the reason that you've got less stuff left over is because some of that's been turned into CO2, water, smoke, other things. So that's all been lost. It still exists. You've just sent it somewhere else, hopefully. Hopefully you're not trapping all your smoke in your house. In non-nuclear chemical reactions, there are some changes in mass, but they're really small and we wouldn't notice them. I don't think that we would be able to measure them in our labs. So our total amount of matter is going to remain constant. This is a fun one because I forgot to change these numbers. That's supposed to be 128. And this is supposed to be 72. Let's say we burn 32 grams of methane on our gas stove. Methane is typically the gas that you've got piped into your house if you've got a gas stove or a gas line. If you burn 32 grams of methane on the gas stove, in theory it reacts with 128 grams of oxygen, O2, just from the air. And that will end up forming 88 grams of carbon dioxide, same stuff that we breathe out, not great to breathe. And it'll also produce 72 grams of water. So before the reaction occurs, the things that are reacting are methane and oxygen. We can see them on the left side here. These are our reactants. And we know how much of the reactants were put in. 32 grams of methane, 128 grams of oxygen. And our products, on the right side, our products are carbon dioxide and H2O, 88 grams, 72 grams respectively. Before the reaction, we had 160 grams of total mass. After the reaction, we still have 160 grams of total mass. Let's say that we've got a different chemical reaction. We have potassium hydroxide, which is KOH for the chemical symbol. This reacts with carbon dioxide, CO2, and then we've got a keyword, to produce. This lets us know that we're now talking about our products. The potassium hydroxide, the carbon dioxide react, so those are our reactants, to produce the things that follow, potassium carbonate and water. So I'll underline these in fuchsia. So those are our products. How many grams, so we got our question word, how many grams of potassium carbonate are produced if, now we've got some givens, 224.4 grams of KOH, reacts with 88.0 grams of CO2. The reaction also produces 36.0 grams of water. So we have a lot of information packed into one question. What we need to do to start this problem, we know it's a conservation of mass problem, because it says up here. What we need to do to start this problem is set up our chemical equation. We need to know what reacts, we need to know what's produced, so that we can set the masses on both sides equal to each other to figure out our one variable. So in our first sentence, right, potassium hydroxide reacts with carbon dioxide. That means those are our reactants. I'm going to use the chemical symbols because it's a lot shorter than writing the whole thing out. So KOH plus CO2. KOH and CO2 are our two reactants. They react to produce. Then we've got two other chemicals, K2CO3, which is potassium carbonate. We also produce water, which is H2O. Any questions about the first part, just setting up that chemical equation? Perfect. Now what we need to do is pair our masses that we were given in the question. This later part, we need to pair these masses with the correct symbols. So 224.4 grams of KOH. We'll just write that in under our KOH. Reacts with 88 grams of CO2, so we'll write in 88.0 grams of CO2. I'll leave the symbol off for now because we're writing it under it. Okay, so these two things react. That's our total mass for our reactants. We're told that the reaction also produces 36 grams of water. So we can write in 36.0 grams under our water. What are we trying to find in this question?
How many grams of K2CO3?
Yeah, we're trying to find grams of this fourth thing, K2CO3, the potassium carbonate. We've got three of the numbers. We're missing one of the numbers. How can we find that last missing number? What important piece of information do we need to know? Something about the left side and the right side. They have to be equal. Have to have the same number of grams on the left side, the reactant side, as we have on the right side, the product side. So we can put a big equal sign in here and add X for our K2CO3. And we've got ourselves an addition algebra problem. We've got two things on the left side. We can add those up, or at least our calculator can. And we've got an extra 36 grams on the right side. We just need to find what X is. Go ahead and give that a try. Hopefully a piece of cake. If not, we'll go through it. All right, so if we add up 224.4 and 88, our reactant amount is 312.4 grams for total for our reactants, which is equal to the amount of products. We don't know how much K2CO3 we have, but we know that we've got 36 grams of H2O. So we need to move that 36 grams from the right side to the left side. To do that, we just equal treatment, subtract, let's do it in blue, subtract 36 grams from both sides. So the 36 grams that we subtracted on the right gets rid of our 36 grams there, and now it's over on the left side. So we subtract 36 from our 312.4, and 276, I know my numbers, 276.4 grams is what X is equal to. So we have 276.4 grams of potassium carbonate K2CO3 that's produced. Questions? Great. Density, which we've already done a little bit with our lab that we did yesterday. Density is a ratio of mass and volume. Ratios are where you divide one thing by another. Or the relationship between one thing and another. Usually when I talk about ratios, there's like some division. Or it might be like a 2-to-1 or a 1 to 2. There's lots of different ways to represent it. But we have an equation. And our equation is that D equals M over V. Density equals mass over volume. Mass often has units of grams. Volume often has units of milliliters or cubic centimeters or cc's. Those are all the same. Density is a fundamental property of substances. And so sometimes in labs, not in our labs very much, but sometimes in labs, we can use density to figure out what chemical we've got. This is helpful for metals. So like for the metals that we had, those unknown cylinders, you could figure out or guess what each of those metals was by calculating its density and then comparing it to literature values of density, and also some other properties like color and stuff. Different substances have different densities, so things like woods, a lot of woods are often going to have low densities compared to things like metal. Lead and mercury notoriously have very high densities. So they feel very heavy for a small amount of the material. If you change the size of an object, if you have a small amount versus a big amount, the density doesn't change because you're scaling both the mass and the volume. Some hijinks happening outside. Okay, if we want to calculate density of a substance, we can use our little formula, D equals M over V. So for an example, a sample of a liquid has a volume of 22.5 milliliters and a mass of 27.2 grams. We want to calculate the density. Okay, so density equals mass over volume. Our volume, we're told 22.5 milliliters. You won't always be told that volume is milliliters. You will have to know sometimes that milliliters or cubic centimeters or cc's is volume. And you should know that grams is mass, but we're told that in this case. So if we want to find it, find our density, it's the wrong color. If we want to find our density, that is equal to our mass, 27.2 grams, divided by 22.5 milliliters. When we do this, we get a bunch of numbers out. This looks like it has 8s continuing on forever. We put a line over it. When we do this, our units cancel or don't cancel? Are grams and milliliters the same thing? Definitely not. They don't cancel, and so they just continue through. We can't just poof disappear units or poof appear units. So the units that we put in are the units that we get out. And grams per milliliter are correct units for density. Is this our final answer? No, it wouldn't be. Why not? Significant figures, SF. So the two numbers that we put in, 27.2, 22.5, these each have 3 significant figures. So we would expect 3 significant figures out for our answer. So 1.2, round that 0 up, 1. 1.21 grams per milliliter. Let's say someone purchases a platinum ring, ooh, fancy, and it has a mass of 9.67 grams and displaces 0.452 centimeters cubed of water. Is that ring genuine? Is it all platinum? The density of platinum is 21.4 grams per cubic centimeter. Give that a try. As a reminder, density equals M over V. What is our first thing that we want to do here? What's something we can start with for solving this problem?
The mass is 9.67.
The mass is 9.67 grams. What else?
The volume is 0.452.
Volume is 0.452
centimeters
cubic centimeters. That's the displaces part. This is like what we did with the nickel beads and the glass beads. We used the displacement of water to figure out the volume. For a ring, this would be helpful because it's hard to figure out exactly the volume of the ring, especially if it's got like bezels and fancy features and stuff. What do we do with these numbers? We divide them, right? Density is mass over volume. Our mass, 9.67 grams. Our volume, 0.452 cubic centimeters. Ask our calculator for some help. Our calculator says, sure, I got you. 21.393800531 grams per cubic centimeter. Then we think, sig figs. Or, yay, sig figs. We look at our numbers that we put in. There are 3 sig figs each. This leading 0 doesn't count. So we round for 3 significant figures. 21.4 grams per cubic centimeter. Is that our answer? No, that's not our answer. What did the question ask? Is the ring genuine? What kind of answer do we give for that? Yes or no, right? Does it look like it's genuine?
Yeah.
It looks like it's genuine. Yes, the density is the same.
So for example, if one of these was on a quiz, the answer wouldn't be the answer, it'd just be a yes or no? Or is it just information?
This is more just like general problem-solving strategy sort of stuff. I wouldn't be able to really leverage this like the trick, I'm doing air quotes, the trick of this question like on an exam because it's multiple choice. But just trying to direct us to like, we want to think about what is the question actually asking us. Okay, other stuff that we can do with density. Density is also useful as a conversion factor. Let's say that we have a liquid substance. It has a density of 1.32 grams per cubic centimeter. What volume should be measured to deliver a mass of 68.4 grams? What are we finding? Are we finding volume or mass? We're finding volume. It's right next to our question word of what. So we're asking what volume should be measured to deliver a mass of 68.4 grams. Oftentimes with questions that have like the wording flipped a little bit like this, where you're given some information at the end, people wrongly assume that we're finding the thing that we're given at the end. That's part of why I talk about we want to look right next to our question word. So we're finding volume. We have both mass and density. We can use those together, using density as a conversion factor to find volume. I like to, for all of my problems, start with the simpler thing that we're given. So we're given something that's got 1 unit, grams. Our mass has grams. Our density has grams per cubic centimeter. I like to start with the one that just has 1 unit, and we use the other one as our conversion factor. Formally, you can do it either way. It doesn't matter the order, but I like to start with simple units. So 68.4 grams. We don't actually need to know what our formula is. We don't have to do algebra if we know how to look at our units to get what we want. So we're starting with grams, and we want to find volume. What's a unit of volume that's relevant here? Centimeters cubed. So we want to get to cubic centimeters. So we need to get rid of our grams and get cubic centimeters, and that's going to be done using this 1.32 grams per cubic centimeter. So it might be helpful for us to rewrite the grams per cubic centimeter part here. So 1.32 grams over cubic centimeters. If we multiply by our density, is that going to get rid of our grams? I'll write it in. If we multiply 1.32 grams over cm3, do these grams cancel? No, they do not, right? They'd be multiplying, so we'd have grams squared over cubic centimeters, which is crazy units. So, just like all our conversion factors, we can flip it. So let's flip it. We'll put the cm3 on the top, the 1.32 grams on the bottom. Now do our grams cancel? Yes, our grams cancel. So grams cancel grams, and what's left is cubic centimeters. So without knowing our density equation, just looking at the units, we were able to get our units to cancel out to get us the units that we wanted. So this tells us we divide 68.4 grams by 1.32, our density, and this will give us 51.8 when we round for 3 significant figures, cubic centimeters. The other way that we could do this is with density equals mass over volume. We can do a little bit of algebra with D equals m over v. The thing that we're finding is volume. In algebra, that means that we want to get volume by itself, and it also needs to be on the top. So currently, volume is on the bottom. It's not by itself. Mass is also there. So we need to get it to move over. We can get it to move over by multiplying both sides by volume. That gets volume to cancel out on the right side. So we've got V equals, or V times D equals M. But we don't have volume by itself yet. We need to move density over. So we divide both sides by density. Density cancels out on the left side. And we get that volume, the thing we're looking for. Volume equals mass over density. So mass divided by density will give us volume. What did we do in this problem? We did mass divided by density. So that would be another way of doing it with a little bit of algebra. There's a third way of doing it that some people like. There's this little triangle method or pyramid method. So D equals m over v. We make this little pyramid. And whichever one of these 3 variables you want, cover it up. So let's say that we want to find mass. Ignore the mass part. How are density and volume related to each other here? They're next to each other, so we multiply them. Density times volume would give us mass. If we wanted to find density, look at how mass and volume, how the other 2 things are related. Ignore the density part. Mass over volume equals density. If we wanted to find volume, mass over density equals volume. So you just cover up the thing that you want, and then how the other 2 things are related is the equation that you use. This is one of 2 equations that this works for. Some people like to use it, so I show it to you. You can use any of these 3 methods. It doesn't matter to me. Questions? We're having a good time. All right. Densities as a conversion factor. This is table 2.4.1 from your book. There's some common densities there. Generally, you do not need to memorize densities. You can just look them up. Oftentimes, if you look them up, they'll be in kilograms per cubic meter, because that's what Google and lots of other people on the internet like to do. If you just divide it by 1,000 or multiply it by 1,000, I don't remember, it'll convert it to grams per milliliter. So you can just look up densities. That's usually what I do. The one density that you want to know for this class, density of water, is what would be the easiest number to remember that's not 0? What's a really easy number? 1. Yep, the density of water is 1-ish grams per milliliter. This isn't always true, but generally it's true. It's true at 25 degrees Celsius, which is room temperature. So normally, water, 1 gram per milliliter. That's just like, I think, really helpful to have in your back pocket. It does come up. I think I usually make one question on it. I think it's a later exam. I'll underline it too so you can tell that it's important. All right, let's do this one as an exercise. That means that I'll have you do it. Calculate the density of a 30.2 milliliter sample of ethyl alcohol. That's one of the ones you can drink, with a mass of 23.71002 grams. So give that a shot. All right, we want to calculate the density given volume and mass. So we're finding density, we're given volume, we're given mass. What is our equation for density? Density equals mass over volume, our mass being 23.71002 grams, our volume being 30.2 milliliters. Put that into our calculator. And we get 0.7851 with units of grams per milliliter. Questions? But Mr. K, what about the sig figs? Thank you for asking, inquisitive student. We've got in our milliliters 3 sig figs. We've got in our grams 7 sig figs. We're going to use the 3 significant figures because that's the smaller amount, meaning that our final answer is 0.785 grams per milliliter.
So it's, you the 0 at the ending with the calculator, you drop it? Or just my calculator that has it?
All calculators, if there's a trailing 0 at the end behind the decimal point, they will drop that 0. It's not always significant, it's not always important. In some cases in lab, like it is important, like when we're doing subtraction especially. All right, so that's density. Energy is another important component. Energy, our definition is that it's the capacity to do work, the ability to do work. If you don't have any energy, it's hard to do work. So energy is our capacity to do work. Work is defined as the result of a force acting over a distance. One funky consequence of that is that if you just like push on a wall and the wall doesn't move, you haven't done any work, even though you'll get tired from pushing on a wall eventually. So that's one funky consequence of the way that work is defined. Force acting over a distance, so pushing on something and the distance that it moves. The thing that we'll talk about more in this class is heat. Heat is a transfer part being important, of energy. Typically, heat is transferred from high temperature to low temperature. So if you leave an ice cube out on the countertop, the ice cube is colder usually than the environment, so energy is going to flow into the ice cube, causing the ice cube to melt. We have insulated, cups and whatnot to prevent that from happening, to keep our ice water nice and cold, or our room temperature water nice and room temperature. Understanding the way that energy moves, the way that energy flows as heat, is important for some problems in chemistry. Energy also has a law of conservation. So we also have the law of conservation of energy. It's very eerily similar to our law of conservation of mass. All that we've swapped out is energy. So energy is also neither created nor destroyed. We cannot create energy out of nothing. It also does not vanish into nothing. The total amount of energy is constant. But one thing that we can do with energy, sort of similar to how we can change mass into other things, like we can change things that are solids into gases and then the gases go away. With energy, we can also change between different types of energy. We'll talk about the forms of energy. I think it's the next slide. And there's also the ability to transfer energy. So here are a couple of forms of energy. We got 5 forms here. Kinetic energy, which is the energy associated with motion, like rolling across the classroom, which before they added carpet into this class, I could roll all the way across the class. It was great, just with one go. But they knew I was getting too powerful, and so they added carpet in to make it so that I couldn't do that. The other consequence of not having carpet is that the chairs were obscenely loud. And now that we have carpet, they're not. So that's actually good that they put carpet in. So that's kinetic energy. There's also potential energy. So like potential could turn into other energy, could turn into kinetic energy or chemical energy. And this is typically associated with position. So we often think of like gravity-related potential energy. So if you have something up really high and it falls, you let go of it or it gets knocked off a shelf, its potential energy gets turned into kinetic energy, and it maybe imparts that kinetic energy into the ground and shatters in the process, depending what it's made of. So that's energy associated with position or composition. Composition more like for this chemical potential energy we'll talk about. There's also electrical energy associated with the flow of electrical charge, the stuff that keeps the lights on, that keeps the projector running, that keeps our phone charged. There's also thermal energy or heat energy. Thermal energy is related to the way that atoms and molecules are vibrating around. So you might remember when we were talking about solid phases of matter, it was all of the atoms and molecules kind of in their own spot, but they're still vibrating around. They have different amounts of energy depending on, or they have different amounts of moving around depending on the amount of energy that they have. So if you have very little energy, you're more likely to just be sitting still. If you've got a lot of energy, you might be fidgeting, moving around in your seat. Atoms and molecules with thermal energy are kind of similar. So, and then our last form of energy that we'll talk about is chemical potential energy. So this is related to positions of particles in a chemical system, like in a molecule. So some molecules are really, really stable. The atoms are super happy in the configuration that they're in, and it's hard to get them to leave that configuration. This is like any number of us, right? If you're in a really snugly cozy bed, you've got nothing to do, it's really nice and comfy in bed, right? You're very comfortable, you're very stable. Getting you out of bed might be quite a chore. If, however, you're lying on a bed of Lego bricks, you're very unhappy in your position, you're very unhappy laying on those Lego bricks, hopefully. And that means it's going to be really easy to get you out of bed. So chemicals have a similar sort of thing. Some molecules are very unstable. They really don't like the configuration that they're in. And if you give them the opportunity, they will leave that configuration. They will undergo a chemical reaction by exploding or decomposing. TNT, fireworks. There's some contact explosives, meaning like if you just hit it too hard, it blows up. Those sort of things are really unstable, and they can release that chemical potential energy pretty easily. Questions about our types of energy? You should be able to identify, like match a definition with the type of energy for this. You don't necessarily have to be able to give an example, but you should be able to match these. All right, so some examples of energy. Here's a picture of the Hoover Dam over here on the right. It's a big dam. The way that dams work, just kind of a for fun thing, right? So dams, giant walls of concrete holding back a large river or a lake or some other body of water typically. That water then begins to pile up, filling up the reservoir. As it piles up, it's gaining elevation. You've got more water there. You're building up potential energy. And then you've got turbines that are inside of the dam. You can open up gates to let water run through, turn that potential energy into kinetic energy. That can then spin a big turbine, and that turbine can generate electrical energy, which powers our homes or whatever. Powers ChatGPT, having people ask it, banal questions or whatever. So this dammed up water has a lot of potential energy, and that can be used to get turned into electrical energy. For energy, we've got a couple of different units. I'm adding the little crook on the J for joule. Joule is our SI, our metric unit of energy. And it's got the capital J for its symbol. We also have the calorie. The calorie, lowercase c cal, is the amount of energy required to raise the temperature of 1 gram of water by 1 degree Celsius. 1 gram of water, 1 milliliter of water, it's a small amount of water. It's the amount of energy to raise that by 1 degree Celsius. That is different from the calorie, the capital C calorie. The capital C calorie is the nutritional calorie. That's the one that you see on the nutrition facts on pieces of food that you eat. Also called a kcal. So lowercase c cal is not the same as uppercase c cal. Uppercase c cal is the one that you are familiar with, the one that you know about. The lowercase c cal is different. So capital C calorie is different from lowercase c calorie. This is sort of similar to the way that with our metric prefixes, we've got lowercase m and uppercase m. Lowercase m is milli, uppercase m is mega. There are other cases, other instances where we'll have an uppercase and a lowercase and they're different. This is one of those details things that I think kind of throws people off a little bit. Okay, so those are 3 of our units of energy, and then there's a 4th unit of energy. There's lots of units of energy, but there's a 4th one we'll talk about, kilowatt hours. These are the ones that your electrical company, assuming you have an electrical company, is using to bill you. Hey, you use this many number of kilowatt hours, so we're going to charge you 76 cents a kilowatt hour. You owe us $500 this month, what have you. We are typically going to be dealing with joules, calories, and calories. We don't really touch kilowatt hours much. They're really landscaping out there. I love it. All right, large light blue sports drink, you know the one I'm talking about, contains 190 calories. How many kilojoules is that? And you've got some energy conversions given to you there. So go ahead and give that a shot. All right, our large light blue sports drink contains 190 calories. We want to find kilojoules. We're given a couple conversion factors. So we're starting with 190 calories, trying to find kilojoules. Hopefully we all correctly identified our start and end points. We might want to build out a solution map. So calories going to kilojoules. What might our first step be?
4.184.
What are we converting to from calories?
Little calories.
Yeah, we're converting to calories. Little c calories. And we can do that with this 1 cal, big cal, not to be confused with the dog or the bear. My friend's dog is named Cal after the bear. So 1 cal equals 1,000 cal. And what can we go to from calories? Joules. We can convert to joules. Can we convert from joules to kilojoules? We sure can. For this cal to joules, we're going to use the 1 lowercase c cal equals 4.184 joules. And 1 kilojoule equals, that kilo means 10 to the 3. So 1 kilojoule is 1,000 joules. And we can now set up our conversions, our calculation. So following our solution map, for our first step, we're converting to cal. 1 big C cal equals 1,000 cal. We have big C cal. We want to get those to cancel, so we're going to put the little C cal on top and the big C cal on the bottom. Those will cancel out. Goodbye, Berkeley. And then for our second step, we're converting from lowercase c cal to joules. So our 1 cal, lowercase c cal, will go on the bottom. And our 4.184 joules goes on top. And then our last step, joules to kilojoules. We're putting the kilojoules on top and the 1,000 joules on the bottom so that joules cancel. And we're left with kilojoules. Any questions about the solution map or the setup for the calculation? There's another fun thing we can do. We've got 1,000 on the top. We've got 1,000 on the bottom. We can make those cancel out too. You don't have to, but it means that you don't have to press as many buttons on your calculator. So we do 190 times 4.184, and it's 794.96. And then we round it. All right, we had 3 sig figs for our first thing. This 1,000 cal is 1 cal, and the 1 kilojoule is 1,000 kilojoules. These are both exact. I believe the 4.184 one is also exact. But worst case scenario, it's 4 sig figs. I just don't remember off the top of my head. Either way, we're using our original 3 sig figs for our answer. Going to look at the 9 to see how we round. This rounds up 795 kilojoules. Final answer. All right. Energy changes often happen when we do chemical changes. Physical and chemical changes both are often accompanied by energy changes. So for example, water evaporating, that takes some energy, thankfully. Natural gas burning, that also involves energy. When you burn natural gas, it heats things up. That's how we cook things if we have a gas stove. The release of the energy during a chemical reaction is like the release of energy when a campfire burns. This one has some like metals in it. That's why there's the fun colors in there. Same reason that fireworks have fun colors. Typically, things that have high potential energy, either by their position or by their chemical orientation, tend to change in a way that lowers their potential energy. High potential energy is unstable. Usually. So things will often try to get rid of that potential energy, lower their potential energy. That's why things fall. That's why some chemicals explode. So things like TNT, trinitrotoluene, undergoes rapid chemical changes to lower its potential energy, which is why TNT is so explosive. It's got a lot of potential energy that it wants to get rid of, and it'll do so vigorously and with very little input. There was a lab that I did when I was in undergrad where we were making some compound, and there was like this side product that we could also make, and we were warned, hey, if you make this side product, it's a contact explosive. If you touch it too hard, it blows up. So don't let anything dry out, because you might have some of that in there, and then it might blow up. Nobody had their thing blow up, but that was, a little bit nerve-wracking for some of us. Okay, so the way that we describe the flow of energy is with these two words, exothermic and endothermic. The thermic part being energy, the exo meaning outside, and the endo meaning inside. In an exothermic reaction, energy is released. Energy goes outside. It touches grass. So for example, when wood burns, bonds in the wood are broken, and those release energy. There's heat that's emitted from an exothermic reaction. In an endothermic reaction, energy is absorbed into the system being the thing that we care about, so the chemical or an instant ice pack, for example. When chemicals in an instant ice pack are mixed, energy is absorbed by the reaction takes energy, so it pulls in, it uses up a lot of energy first. That's what makes it really cold. And then it continues to pull in energy to help continue to drive the reaction because it uses up a lot of energy. crunchy? Why are bugs crunchy? Their skeletons on the outside, they have an exoskeleton. Bugs have an exoskeleton, crunchy bits are on the outside. We have not an exoskeleton, just a skeleton. We might call it an endoskeleton. So our crunchy bits are on the inside. Exoskeleton outside like a bug. Energy is being released. Energy is going outside. Any questions about exothermic or endothermic? All right, fun skeleton fact. Inside each and every one of us is a complete human skeleton. There's our spooky fact for the day. All right, each of these processes is energy going in, endothermic, or is energy coming out or being released, exothermic. So if you want to get water to boil, is that an endothermic process or an exothermic process? That is an endothermic process. You have to put energy in to get the water to boil. You have to heat water to boil it. And it takes a lot of energy. What about gasoline burning? Is that endothermic or exothermic? Exothermic. This is why your car has systems in it to cool it down. If you drive your car for a little bit or you run the engine for a little bit and you go over and feel the hood, it's really warm, it's really hot, that's a lot of that extra heat that just hasn't been released yet. What about ice forming on a pond? Is the ice forming exothermic or endothermic?
How does it form a bond?
It's cold outside. In this example, it's not cold outside right now. So if ice is forming, is the water gaining or losing heat? It's losing heat. So it's exothermic. This one always trips people up. So the liquid water loses heat to become ice. If we wanted to, we could make a little like energy graph. I want to, so I'm going to. So energy. If we think about our three phases of matter, our three states of matter, what's our lowest energy state of matter? What's our coldest state of matter? Solid. What has a little bit more energy than a solid? Liquid. Liquid is hotter than a solid, right? Like ice, liquid water. And then what has even more energy or what is hotter than a liquid? Gas. So if we think about ice forming on a pond, we're going from a liquid to ice, a solid. So we have to go down in energy. So it has to lose energy somewhere. In the case of ice forming on a pond, it's releasing that energy. We're losing that energy to the environment because it's just colder outside. So liquid water to ice. It has to lose energy or lose temperature or lose heat. Temperature in energy are related. In the case of our water boiling, we were changing liquid water to vapor water, gas. So we were increasing the energy. We had to put energy in, so it was endothermic. Questions about endothermic, exothermic? All right, we've mastered it. Perfect. Let's talk about temperature now. So as I said, temperature is related to thermal energy, or just energy generally. Temperature is a measure of thermal energy. It's not the same as the amount of thermal energy. Strictly speaking, you don't have to transfer any energy to measure a temperature. For all intents and purposes, though, we do actually have to do some of that just because like the way that the world works. But within anything that's not at the absolute coldest zero energy that it can be, the atoms and molecules are vibrating around a little bit. In the case of solids, they're vibrating around in their spot. They're people eating their snacks at a movie theater. In the case of a liquid, they're able to move past each other. They've got a little bit more thermal energy. They've been able to separate from their neighbors a little bit. And in a gas, they have the most energy. They completely separate from each other. But this is an important idea that atoms and molecules are always in constant, somewhat random motion. The hotter the temperature, the more the energy, the more the moving around. Some people are really fidgety. They've got a lot of energy. They got to fidget that energy away. Other people, perfectly happy to just sit in one spot looking at a fly on the wall for 5 hours. No energy. So heat is our flow of thermal energy. It's a transfer of energy. Heat is transferred from high to low. Things with a lot of thermal energy transfer their thermal energy to things with little thermal energy, so like an ice cube absorbing energy. Or if you put a piece of cold ice instead of a piece of warm ice, if you put a piece of cold ice into a cup of warm water, the ice cube has less thermal energy, so it absorbs energy from the water that's around it. And that cools down your water. That's how ice works. Temperature is a measure of thermal energy, but there's usually a little bit of heat exchanged as well. We have 3 different temperature scales. Who can give me one temperature unit? Fahrenheit. Who can give me another temperature unit? Celsius. Does anyone know the third temperature unit? Kelvin. So we've got Fahrenheit, Celsius, and Kelvin. And I'm going to go back and check the thermometer back here because the room temperature does vary. It is 74 degrees Fahrenheit in here apparently. Oftentimes it's a little bit colder than that. Usually it's around 72 degrees Fahrenheit. Most places you'll see 75 degrees Fahrenheit. So there's a little bit of plus or minus. It's just me being silly. But usually 75 Fahrenheit is what people are talking about when they talk about room temperature. 25 degrees Celsius is often what people are talking about in Celsius for room temperature. So the Fahrenheit scale, this is the one that we know that we use. The Celsius scale is the one that pretty much the entire rest of the world uses. And then in some scientific applications, we'll use Kelvin. Kelvin is different from Fahrenheit and Celsius. Kelvin assigns 0 Kelvin. Notice that there's no degree sign. So we don't have to use a degree sign for Kelvin, which is nice for typing it. So there's no degree sign for Kelvin, and it assigns 0 Kelvin to the coldest temperature possible, which would be absolute 0. So that would be no thermal energy. I've heard Fahrenheit and Celsius described as Fahrenheit is how we feel. So 100 degrees Fahrenheit is really hot, 0 degrees Fahrenheit is really cold. That's how we would feel. Celsius is a temperature scale based on how water feels. At 0 degrees Celsius, water is freezing. At 100 degrees Celsius, water is boiling. Another important thing to note is that degrees Celsius and Kelvin, those units, are the same size unit. Fahrenheit is a different size unit than Celsius and Kelvin. Celsius and Kelvin are bigger units. And there's some important temperatures to know. So for example, the boiling point of water in Fahrenheit is 212, which is not the easiest to memorize. You might have it memorized. Celsius, it's 100. Nice and easy. For freezing point for water at Fahrenheit is 32 Fahrenheit. Not necessarily the easiest to memorize. And in Celsius, it's 0. So 0 for freezing, 100 for boiling for water. Makes Celsius pretty convenient in those ways. We have questions about our temperature scales. Confusions? Contusions? Perfect. We can convert between Fahrenheit, Celsius, and Kelvin with these following formulas. So if you want to find Kelvin, add 273.15 to whatever your Celsius value is, and you're in Kelvin. If you want to convert to degrees Celsius, take your degrees Fahrenheit, subtract 32. 32 is the difference between the boiling points, or the freezing points. This is just extra fun, optional information. And then divide by 1.8. 1.8 is the ratio of boiling point minus freezing point for the two scales. So the difference between freezing and boiling in Fahrenheit is 180, and the difference between freezing and boiling in Celsius is 100. So 180 divided by 100, 1.8. That's where those numbers come from. If you want to work in the other direction, if you want to find degrees Fahrenheit, you have to rearrange this equation. I think I might have that in here, because the order of operations is important for that one, and people often mess up. I forgot to take a break. Sorry. Converting 47.5 Kelvin to Celsius. You can refer to your yellow sheet. You can refer to the equation up here. So let's write it down. Kelvin equals degrees Celsius plus 273.15. So we are trying to find Celsius. That means we need Celsius by itself. We're going to rearrange by subtracting 273.15 from both sides. So Kelvin minus 273.15 equals degrees Celsius. So degrees Celsius here is 47.5. I usually just leave off the units for these, minus 273.15. So So it's negative 225.7 after we round. For 1 decimal place. So another thing that I forgot to mention about Kelvin is that you cannot have negative Kelvin. That's another quirk about Kelvin, because 0 is said to be the lowest absolute energy, no energy. You can't have less than no energy, believe it or not. Can't have less than no energy, so 0 is the lowest that we can go in the Kelvin scale. So one way that we can check ourselves, if you plug stuff in and you get negative Kelvin, there should be a little warning bell going off in your brain. We can't have negative Kelvin. This must be wrong. Check it again. So that can be one of the ways that we can check ourselves on temperature conversions. Let's say that we want to convert Fahrenheit 451 to Celsius. So 451 Fahrenheit to Celsius. Our equation, degrees Celsius equals degrees Fahrenheit minus 32 over 1.8. This one's already set up to convert to Celsius. So degrees Celsius equals 451, the temperature that paper catches on fire, allegedly, minus 32 over 1.8. So let's see what temperature Celsius paper burns. Go ahead and put that in your calculator, give it a shot. Who got 433? Anyone get 433 Celsius? Nobody got 433 Celsius? $433.2 repeating. Some people get that? All right, you put it in your calculator wrong. That's why I wanted you to put this into your calculator. There's no shame, no smoke, no shade. Just there was an important thing that we left off. Parentheses. You have to put these parentheses in your calculator. Otherwise, it's going to do it differently than how you want it to. Or you can do 451 minus 32, hit enter, then divide by 1.8. 232.7 repeating is what we want. Okay, so if you put in, without parentheses, 451 minus 32 divided by 1.8, the reason that this is wrong is your calculator does PEMDAS perfectly. It does parentheses first. We didn't put in any parentheses. Then it skips exponents because there's no exponents either. Then it does multiplication division. So your calculator for its first step, 32 over 1.8, then it'll subtract that from 451. And that's not what we wanted, right? Correct. That's not what we wanted. What we wanted was do the subtraction first and then multiply that by 1.8. So this top one is wrong. This bottom one is correct. And this bottom one will give us 232.7. Put a line over it so we know that it's repeating, apparently forever, degrees Celsius. And then for significant figures purposes, we'd round this off to 3 significant figures. Questions? All right, let's say that we want to go the opposite direction. We want to convert 115 degrees Fahrenheit to Kelvin. Starting with degrees Fahrenheit, going to Kelvin. Our equations are something like this. It's over 1.8. And Kelvin equals degrees Celsius plus 273.15. So we can just do these in order. We can convert to degrees Celsius, then from degrees Celsius we can convert to Kelvin. So 115 minus 32, press enter, or have parentheses, divide by 1.8. 46.1, that one repeats. Usually if it just does the same thing over and over until the end of the calculator, or if it like rounds up maybe, that just means that it repeats forever. So that's probably what's happening there. And so then we can put that into our second equation here. 46.1 repeating plus 273.15. Anytime that you want to put in that whatever thing repeating, you just press it until your calculator stops letting you press it, basically. Or you take the previous answer and use that. That gives us 319.261, and that one looks like it's repeating. Our unit would be Kelvin. How many significant figures should we have? Somebody said 3. We have any other guesses? 2? Did somebody say 5? I thought I heard 5, but I'm glad that I didn't. Okay. I'm making stuff up again. The correct number is 2. Why is the correct number 2, Mr. K? Tell us. All right, do 115 minus 32. That's our first step, right? What do we get as our intermediate answer from that? 83 with 0 decimal places. We've got 2 numbers, 2 non-zero numbers, 2 significant figures. Sorry, it is 3 significant figures. I'm clowning. This is what I get for not taking a break. 2 significant figures divided by 1.8. So this 6 is our last significant figure. And then we do addition. And so we have 0 decimal places, so the 9 is our last significant figure. We got rid of a significant figure, and then we added it back, apparently. So 319 Kelvin. Very cool. All right, one more thing that I'd like to show us, because I don't remember which direction I give you for degrees Celsius and degrees Fahrenheit. If we wanted to convert the other direction, if we wanted to find degrees Fahrenheit from degrees Celsius, we can do that with this equation. We have to get our order of operations correct. So we want to get degrees Fahrenheit by itself. So for finding degrees Fahrenheit. Some of you, it may have been a while since you took algebra. Maybe you didn't like it. Maybe you still don't like it. Understandable. But we do need to be able to do a little bit of algebra sometimes in this class. So finding degrees Fahrenheit, we want degrees Fahrenheit by itself on its own side. So we need to move the 1.8 and the 32 over to the left side. We have to do one of those first. So we have to move the 32 or the 1.8 first. Who knows which one we're moving first? We're moving the 1.8 first. So we have to times by 1.8 first. If you try to move the 32 first, doesn't work. Or it's unnecessarily complicated if you do. So we move the 1.8 first. We get 1.8 times degrees Celsius equals degrees Fahrenheit minus 32. And now we can move the 32. So add 32 to both sides. The 32's cancel on the right side. I'm going to flip them left and right. So degrees Fahrenheit equals 32 plus 1.8 times degrees Celsius. Anytime that you're doing a temperature conversion problem and you just want to check, hey, did I do stuff right? Google knows. Just ask Google. But remember that you can't ask Google on the exam. So use that to check your work only. Questions? All right, we're almost done with chapter 2. We've got one more set of important ideas to talk about, and that's heat capacity. Every substance changes temperature when it's heated. Some things heat up very quickly, like metals heat up very quickly. If you put an empty pan on the stove and you heat it up, you turn the burner on, it's going to get really hot really fast. If you were somehow able to magically float water over your stove and try to heat that up, even if it's the same mass as the pan, it's going to take a lot longer to heat up that water to the same temperature as the pan. It takes a lot more energy. Food at a restaurant is one example of this. If you order a nice plate of food at a restaurant, maybe you've got a steak, you've got potatoes, you've got a salad. The salad's going to be nice and cool. The potatoes and the meat are hopefully going to be coming out hot. Those are going to cool down or change temperature at different rates. What's the one that's going to cool down the fastest? Ignore the salad. What's going to cool down faster, mashed potatoes or a steak? Do we know? The steak is going to cool down like so much faster than mashed potatoes. There's a reason that the game is called hot potato and not hot steak. Right? The hot potato stays hot for a long time. It's got a lot of water in it. It's going to change temperature much more slowly than the steak. The steak is going to cool down pretty quick. So if you want to get the most out of your steak, start on it right away. Don't wait until you've eaten your salad and your mashed potatoes completely before you start on the steak. So that's just an example of heat capacity. So heat capacity is the amount of heat. How many joules, how much temperature basically do we have to put into it to change the temperature by a given amount by 1 degree Celsius? Hope you didn't get too attached to heat capacity. We're probably never going to use it again. Why? It's this given amount part. So that's just like any amount that you want, 5 grams, 10 grams, 2 grams. That's not particularly helpful because we usually don't have exactly that amount of grams. And so we're often going to instead use specific heat capacity. The specific part of specific heat capacity is we've specified 1 gram of the substance. We're going to change 1 gram of the substance. This lets us apply it to any amount of the substance that we want. So instead of heating up 15 grams and it has this heat capacity, we can say for every 1 gram, it's going to heat up by this amount, which helps it apply a lot more. This is going to have units of joules per gram degrees Celsius. This is joules over grams times degrees Celsius. Even though it might look like we're multiplying by the degrees Celsius, it is on the bottom. So that's an important note. We do calculations with specific heat capacity. Here's some examples of specific heat capacity values. On these, for specific heat capacity, higher value means slower to heat up. So a really low value means it'll heat up really quickly. So let's look at some examples. You might also need some of these for your homework problems. It's table 2.6.2.1 from the online book. So water here up at the top has a specific heat capacity of 4.18 as a liquid. This is a really high value, even though it doesn't look like a big number. Compared to lead down here, which is 0.129, or gold 0.129, copper 0.385. Right. Metals typically have really low values because they don't have a very high specific heat capacity. They'll heat up very quickly, very rapidly, with a little bit of heat. They conduct heat very well. This has some applications to why it gets really hot here in the summer. So our average temperature in August for San Francisco, 68 degrees Fahrenheit. This might not be true anymore, but at least it used to be. Must be nice. Our average heat capacity for Fresno area in August, 97 degrees Fahrenheit. That's a lot hotter. Why? Any ideas why? Yeah. Because of the water. Yeah. That's exactly right. So in San Francisco being on a peninsula, has a lot of water around it. An insane amount of water, an unfathomable amount of water, and it's also cold water. It's really cold water because it's coming in from further up, it's coming in from the Arctic. It hasn't had time to warm up very much. That water has a high heat capacity, and so it can absorb a lot of the energy that would otherwise just be floating around in the air. You also get the nice breezes that come in and kind of displace that hot air. So San Francisco has a lot of localized cooling, whereas here in Fresno, we've got just dirt. Dirt doesn't have a particularly high heat capacity. It's not going to soak into the dirt very far. If you dig under a couple inches, it's relatively cool, versus if you've got millions of gallons of water next to you. Another place that you'll find, or a way that you can experience this heat capacity stuff, is if you walk by somebody's yard and they're watering their yard, you'll notice the temperature drop significantly. If you're driving out in the countryside next to like a cornfield, corn has a lot of water in it. It absorbs a lot of the energy. And so it'll tend to be a couple of degrees cooler around a lot of plants, or if there's a lot of water or somebody's been watering. So that's all just for fun stuff. We can do calculations with heat and temperature using this equation. In this equation, Q is heat. Q equals M times C times delta T. M stands for mass. C stands for specific heat capacity. And delta T, T for temperature. And the triangle here is delta. which means change in maths. So this means change in temperature. And change in temperature is given here. So final temperature minus initial temperature. This is an equation that we'll use in lab 2, which is our calorimetry lab. Experiment 2, not lab 2. And you'll also see it on the exam whenever we have that. So let's use this equation. Let's look at an example problem how we would use this. So Q equals mc delta T. In this question, in this problem, looking at the first sentence, just the first sentence, what are we finding? We are finding quantity of heat. What is heat in our equation Q equals mc delta T? Who remembers? Q. So we're finding Q. What are we given? We're told that it's iron metal. We're given 150 grams. So we're given mass. We're also given 2 temperatures. Where do those temperatures fit in? Goes into delta T. For delta T, we have an equation, TF minus TI, the final temperature minus the initial temperature. Which of these 2 temperatures is our final temperature? It's a 73.3 degrees Celsius. So 73.3 degrees Celsius, and we would be subtracting 25 degrees Celsius. You might be thinking that's because the low temperature is going to be the initial, the high temperature is going to be the final. That's not always the case. Sometimes our temperature will be going down. So the way that we can figure this out for sure is the language in the text. So from indicates that this is our initial temperature. So from this initial temperature to, meaning that this is our final temperature, 73.3 degrees Celsius. Okay, so we've got TF and TI, so we can calculate delta T. What are we missing to solve this problem? We've got M, we've got delta T, we're finding Q. What's the last thing? C, our specific heat capacity. Yes, our specific heat capacity. So we have to go find a table. Look, a table. So in our table, iron has a specific heat capacity of 0.449 joules per gram degree Celsius. You will be given specific heat capacities on the exam, should you need them. So 0.449 is our C. All right, now we have all of the pieces, all the parts to solve this problem. The first thing that we'll want to do is find our delta T. So delta T equals 73.3 minus 25.0. We get a value of 48.3 degrees Celsius. And that has the correct number of significant figures. We did subtraction, 1 decimal place. So 48.3, we've got 3 sig figs. And then for Q, this is equal to M, 150.0 grams, times C, 0.449 joules per gram degrees Celsius, times 48.3 degrees Celsius. And then we make sure that our units cancel. We've got grams on top, grams on bottom. So those grams cancel. We've got degrees Celsius on top, degrees Celsius on bottom. So those cancel. And we're left with joules. Joules is a unit of heat. So that's good. We can plug in 150 times 0.449 times 48.3. 3,253.005 joules. And then we'd have to round it for significant figures, which is 3. So 3250, turn it into scientific notation. 3.25 times 10 to the third joules. So if this question were on the exam, what you would see for one of your answers, they would probably mostly be in scientific notation. So 3.25 times 10 to the 3 joules is what you'd be looking for. Questions about the first part? Because that's the first part, the first sentence. Okay, what is the direction of heat flow? Is it endothermic or is it exothermic? Was heat flowing into the metal? Was heat flowing out of the metal? Did the metal gain energy or did the metal lose energy? It gained energy. Heat flowed into the metal. This is endothermic. And we know that it's endothermic because the temperature increased. It went from 25 degrees Celsius to 73.3 degrees Celsius. We also know that it's endothermic because our joules is positive. A positive Q value means endothermic. A negative Q value means exothermic. It's losing energy. So positive Q, we're gaining energy. Negative Q, we're losing energy. And we've got one more slide. Ice. A large block of ice absorbs 858 kilojoules of heat as it warms from negative 37 degrees Celsius to 4 degrees Celsius. What is the mass of the block of ice? I'll give you the C value. 4.184 joules per gram degrees Celsius. Q equals MC delta T. Delta T equals TF minus TI. Give it a shot. All right. What information are we given? Actually, first, who's got a guess? Who wants to put some skin in the game? Give me a guess for their answer for this question. Any guessers in the chat?
0, 1,
Say that again.
2, 0, 1.
201. Does that have units?
That's what I was like.
Anyone else?
I also got like around 200 grams, but
0.01.
Around 200 grams. All right, let's find out. So we're given some information. We're given kilojoules of heat. We are given some temperatures. Again, using our keywords. This is our initial temperature of negative 37 degrees Celsius, and 4 degrees Celsius is our final temperature. And I provided you with C value, the specific heat capacity. We're solving for mass, Q equals mc delta T, so we'll have to do a little bit of algebra, a little bit of rearranging. I like to do it first, but I'm also a little bit algebra pilled, so you might choose to do it differently. So to find m, we want m to be by itself, mass all by itself on its own side, and in the numerator that's up top, not being divided under anything. So to perform that, we'll divide both sides by C delta T. That'll move C and delta T from the right side. So mass is equal to Q over C times delta T. We'll also need to figure out what our delta T is. We've got our Ti, our Tf, so we can plug that into our delta T equation. So delta T is final temperature, 4 degrees Celsius, minus initial temperature, negative 37 degrees Celsius. That means we're adding them. So negative, subtracting a negative. This is the same as 4 plus 37. So 41 degrees Celsius. And then plug it all in. So mass equals Q, 858 kilojoules divided by our C value. Our C value is 4.184 joules per gram degrees Celsius. We're also dividing by that 41 degrees Celsius. Things get a little bit hairy here because we've got things that are getting divided in down here. But let's work on canceling out some of our units. Degrees Celsius and degrees Celsius cancel. They're both on the bottom, but one's on the bottom. So those cancel. The grams, since we're dividing and dividing again, this actually goes up to the top. So grams is secretly on top. So let's rewrite this. I'm just going to rewrite it for our clarity. 858 kilojoules. We said that grams is also up here. And on the bottom, we've got 4.184 joules times 41, and we already got rid of those units. Do we have any other units to cancel? Insert Roblox oof sound. It looks like some of us maybe forgot to check and make sure our units cancel out. So what we have to do, we're given kilojoules, we have to convert this kilojoules before we use it so that it cancels out with the joules. So that was a step that I think some of us missed. This is part of why we want to make sure we're writing out our units all of the time. Okay, so let's figure out what that's going to be. 858 kilojoules. 1 kilojoule is equal to 1,000 joules because the kilo means 1,000. So 858,000 joules. So we can instead plug in 858,000 joules. Now the joules cancel, and we can do the calculation. Do we have questions about that? The easiest thing for us to do would be to look at our units before we get started and see that we've got, in our C value, we've got joules, and we are given kilojoules. We want those to be the same, so we could convert the kilojoules before we start doing the rest of it. So 858,000 divide by 4.184, also divide by 41. And it's 5,001.63224 grams. So this would be like a 10-pound block of ice, 11-pound block of ice. For significant figures, we'd round it to 2. So we'd have to put it in scientific notation, 5.0 times 10 to the 3 grams. Questions? Confusions? Smart remarks? Okay, then that'll do it for Chapter 2. We'll start Chapter 3 next week.